Welcome to Sleepy Earth Channel. Have you ever wondered what would happen if the rain never stopped? Not for days, not for years, but for millions of years. Tonight, we're traveling deep into Earth's ancient past to explore endless storms, drowned forests, prehistoric oceans, and the strange creatures that somehow survived beneath dark skies and never-ending rain. Before we begin, what's the longest rainstorm you've ever experienced? And what city are you watching from tonight? Let me know down in the comments. Hundreds of millions of years before dinosaurs thundered across the earth, before forests covered the continents, before birds, mammals, or even flowers existed, this planet may have looked less like the world we know and more like an endless storm trapped beneath a dark sky. Imagine standing on the surface of the ancient Earth nearly 4 billion years ago. There are no green landscapes, no grass moving in the wind, no quiet oceans reflecting sunlight. The ground is black, fractured, unstable, still cooling from unimaginable violence. Volcanoes rip open the horizon constantly, releasing enormous clouds of steam, ash, sulfur, and gases into an atmosphere so thick and hostile that sunlight barely reaches the surface clearly. Above it all hangs an ocean of clouds unlike anything modern humans have ever seen. And then the rain begins. Not the kind of rain that passes overnight, not the kind tied to seasons. This is rain falling onto a world that has barely stopped burning. Rain that may have continued for thousands, perhaps even millions of years, as the planet slowly cooled enough for water vapor to condense out of the atmosphere. Some scientists believe Earth's early skies carried extraordinary amounts of moisture because the young planet was far hotter than today, with oceans possibly evaporating repeatedly under the heat of impacts and volcanic activity. In that kind of environment, the boundary between ocean and sky may have felt strangely temporary. Water rose constantly into the atmosphere, only to fall again in relentless cycles. The strange thing is that without this violent age of storms, Earth might never have become habitable at all. Modern life depends on oceans, rivers, weather systems, and stable temperatures. Yet, those systems were born from chaos powerful enough to erase entire landscapes. Early Earth was not calm when life began preparing itself. It was unstable, loud, flooded, and probably terrifying beyond imagination. Some researchers even suspect that during certain periods, thick global cloud layers may have covered enormous portions of the planet for extremely long stretches of time, creating a dim world where direct sunlight was rare in many regions. If that idea is even partially correct, then the first chapter of Earth's history was not blue skies and shallow seas. It was grayness. Endless grayness, broken by lightning powerful enough to illuminate entire horizons. And lightning itself may have mattered more than people realize. For decades, scientists have debated how non-living chemistry crossed the line into biology. One possibility is that electrical storms in the early atmosphere helped create some of the organic molecules necessary for life. The famous Miller-Urey experiment in the 1950s demonstrated that under certain conditions, electrical discharges interacting with simple gases could produce amino acids, the building blocks of proteins. The experiment did not create life, and modern scientists debate how accurately it reflects the true atmosphere of ancient Earth. But it revealed something important. Storms may not have simply threatened early life. They may have helped prepare the stage for it. That changes the emotional feeling of rain entirely. Instead of seeing storms as destruction, early Earth suggests something stranger. Water, heat, pressure, and instability may have been necessary ingredients in the long process that eventually allowed biology to emerge. But this ancient world was still incredibly dangerous. Around 4 billion years ago, Earth experienced what scientists sometimes call the Late Heavy Bombardment, a period when massive asteroids and debris struck the inner solar system repeatedly. Some impacts would have been powerful enough to boil oceans locally, or even globally, depending on their scale. Imagine what that means visually. Entire seas flash into steam. The sky thickens again. Darkness spreads through the atmosphere. Then, eventually, the planet cools once more, and the rain returns. Again and again, the Earth may have shifted between fire and water, like a machine struggling to stabilize itself. And yet, somehow, beneath all of this violence, chemistry continued moving forward. One of the most fascinating possibilities is that life may not have started in shallow pools exposed to sunlight at all. Many scientists now consider deep ocean hydrothermal vents to be strong candidates for the birthplace of early life. In those environments, sunlight becomes almost irrelevant. Entire ecosystems survive around heat and chemicals rising from beneath the sea floor. Even today, strange creatures live near these vents in total darkness, supported by bacteria that gain energy chemically instead of through photosynthesis. If similar systems existed on the ancient Earth, they may have offered shelter from the unstable surface above. While storms battered the oceans and impacts scarred continents, tiny primitive organisms could have survived deep underwater, hidden beneath miles of Black Sea. There is something unsettling about that possibility because it suggests life on Earth may have begun not in paradise, but underground and underwater, avoiding the planet itself until conditions became less hostile. And conditions were hostile for an incredibly long time. Oxygen was almost absent from the atmosphere during much of Earth's early history. The air would have been toxic to modern humans. The oceans themselves may have contained dissolved iron in enormous quantities, giving parts of the water a strange greenish or rusty appearance. Some ancient shorelines may have looked completely alien compared to modern beaches. Black volcanic rock, red mineral deposits, steam rising from cracks in the ground, rain falling into warm oceans beneath thick clouds, no birds, no trees, no animal sounds at all, just water, wind, thunder, and stone. Yet despite how dead this world appears from a human perspective, it was slowly becoming biologically active. Tiny microbial life forms likely spread through the oceans long before complex organisms appeared. Some of these microbes may have formed layered structures called stromatolites, which still exist in rare places today. These formations are among the oldest widely accepted signs of life on Earth. It is strange to think that for most of Earth's history, life was microscopic. The planet spent billions of years dominated not by giant animals or intelligent beings, but by bacteria quietly reshaping the atmosphere, molecule by molecule. In fact, one of the greatest transformations in Earth's history came from organisms so small they were invisible to the naked eye. Cyanobacteria gradually began producing oxygen through photosynthesis, releasing it into the oceans and atmosphere over immense spans of time. But even this process may not have created a beautiful world immediately. Oxygen was toxic to many early organisms. Entire ecosystems may have collapsed as atmospheric chemistry slowly changed. Some scientists refer to this transition as the Great Oxidation Event, and it may have triggered catastrophic environmental shifts alongside enormous evolutionary opportunities. Earth was not becoming stable. It was becoming different. That pattern repeats constantly throughout the planet's history. Stability is often temporary. Life survives because it adapts to instability faster than extinction can erase it completely. And rain itself may have played a deeper role in this transformation than we usually imagine. Water erodes continents, transports minerals, cools volcanic regions, regulates climate, and shapes chemical cycles essential for biology. Without continuous rainfall over geological timescales, nutrients may not have circulated through oceans and coastlines in the same way. The very landscapes that eventually supported forests and animals were carved slowly by ancient weather systems operating across millions of years. Even today, rain acts almost like the bloodstream of the planet, moving heat and material across enormous distances. On the ancient Earth, that system may have been even more extreme. Some climate models suggest that greenhouse conditions during certain prehistoric eras could have intensified global rainfall dramatically compared to modern averages. Warm atmospheres hold more moisture, which means hotter Earths often become wetter Earths. That relationship matters because it hints at a world where storms were not occasional disasters. They were part of the planet's operating system. And if the clouds truly dominated the sky for vast stretches of time, early evolution may have unfolded under dim light conditions far more often than we instinctively imagine. Creatures that eventually evolved in these environments may have relied less on long-distance vision and more on chemical sensing, vibration, pressure, and environmental awareness. In some ways, life may have learned to feel the world before it ever clearly saw it. There is also another possibility that makes the ancient Earth feel even stranger. Some researchers believe the young sun was significantly dimmer billions of years ago than it is today, a puzzle known as the faint young sun paradox. If the sun was weaker, Earth should theoretically have been frozen, but geological evidence suggests liquid water still existed. One explanation is that greenhouse gases trapped enough heat to keep the planet warm despite reduced solar output. If true, then Earth may have survived through a delicate balance between darkness and heat, clouds and oceans, volcanic gases and rainfall. The world was not simply wet, it was balanced on the edge of multiple competing forces. And somehow, life emerged in the middle of all of them. Maybe that is the most important feeling hidden inside Earth's earliest history. Life did not appear after the chaos ended. It appeared during the chaos, before calm skies, before stable continents, before clean air, before forests, before anything recognizable. The first living systems on this planet may have formed while rain hammered volcanic oceans beneath dark clouds stretching endlessly across the sky. And if that is true, then perhaps life is more resilient than humans usually dare to imagine. Long before forests covered the continents, before fish swam through coral reefs, before anything with eyes, bones, or teeth existed, the most important living things on Earth may have spent their entire existence in complete darkness beneath an ocean so alien that modern humans would barely recognize it as part of the same planet. Imagine descending slowly through the waters of the ancient Earth more than 3.5 billion years ago. The surface above is almost invisible now, swallowed by thick black water filled with volcanic minerals, drifting particles, and heat rising from cracks deep below the crust. There are no whales singing through the sea, no schools of silver fish flashing through sunlight, no colorful reefs. The ocean feels empty at first, almost dead, but the deeper you go, the stranger the world becomes. Far beneath the violent storms and endless rain of the surface, the seafloor begins to glow faintly in the darkness. Towers of black smoke rise from hydrothermal vents like underwater chimneys erupting directly from the planet's interior. Superheated water, rich with dissolved metals, blasts into the freezing sea, creating an environment that should be impossible for life. And yet, even today, some of the most resilient ecosystems on Earth survive around these vents without any dependence on sunlight at all. Entire communities of organisms live there through chemistry instead of photosynthesis, feeding on energy released from reactions involving sulfur, hydrogen, iron, and minerals from deep inside the Earth. That realization changed the way scientists think about the origin of life itself. For a long time, many researchers imagined life beginning in warm, shallow pools, exposed to lightning and sunlight near the surface. But hydrothermal vents introduced another possibility, one that feels almost unsettling in its implications. Maybe life did not emerge under open skies. Maybe the first living systems spent their existence hidden from the sky completely. In some ways, that idea makes ancient Earth feel lonelier. The surface world above was unstable, flooded, and violent. But far below the storms, the oceans may have become shelters where chemistry could slowly organize itself into something more complex. Hydrothermal vents create steep chemical gradients and continuous energy flow, conditions many scientists consider extremely important for early biological processes. Some researchers believe microscopic compartments within mineral structures near these vents could have acted almost like primitive natural laboratories, concentrating organic molecules long enough for increasingly complex reactions to occur. No one knows exactly how life crossed the line between chemistry and biology, and there is still enormous debate about the details. But what matters is this: the earliest ancestors of every living thing on Earth may have evolved in darkness before sunlight became central to life. That changes the emotional image of evolution entirely. The first organisms were not heroic creatures conquering the world above. They were survivors hiding inside a hostile planet. And hostile is probably not a strong enough word for the ancient oceans. Modern seas feel balanced compared to what existed billions of years ago. Early Earth's oceans were likely warmer in many regions, more acidic in certain periods, and filled with dissolved minerals released by intense volcanic activity. Oxygen was almost non-existent. To modern animals, the water itself would have been poisonous, but to primitive microorganisms, these conditions were simply normal. Life adapts to the environment it is born into, not the environment humans prefer. Some of the oldest evidence for life comes from ancient rock formations in places like Western Australia and Greenland, where scientists have discovered structures and chemical signatures that may date back more than 3.5 billion years. Even these findings remain debated because studying such ancient rocks is incredibly difficult. Earth constantly recycles its crust through tectonic activity, erosion, heat, and pressure, meaning much of the planet's earliest history has literally been erased. What remains are fragments, shadows, mineral clues buried inside stone older than almost anything humans can easily comprehend. That uncertainty adds another layer of mystery to the oceans of the ancient Earth. We are trying to reconstruct a world that barely left records behind. But some patterns continue appearing. Water mattered, heat mattered, chemistry mattered, and time mattered more than anything. Life did not explode into complexity overnight. For most of Earth's history, biology remained microscopic. The oceans were dominated by bacteria and archaea, so tiny that entire continents could rise and sink while evolution barely changed visibly at all. If a modern human somehow visited the Earth 2 or even 3 billion years ago, the planet might appear almost lifeless from the surface, despite being biologically active beneath the water. That may be one of the strangest truths in Earth's history. For billions of years, the planet was alive without looking alive. And the oceans themselves may have looked hauntingly different from modern seas. Some scientists believe dissolved iron was so abundant that parts of the water may have carried dark green, rusty, or murky tones. Without oxygen filling the atmosphere, iron remained dissolved in seawater rather than forming rust deposits immediately. Only later, when oxygen-producing microorganisms began changing the chemistry of the planet, did enormous iron formations start precipitating onto the sea floor, creating layered rocks that still exist today. Those formations are like geological fingerprints left behind by invisible organisms that slowly transformed the atmosphere. It is difficult to overstate how revolutionary that transformation was. Tiny microbes altered an entire planet. But before oxygen changed everything, Earth belonged to anaerobic life forms, adapted to low oxygen environments humans would find impossible to survive in. Some of those ancient metabolic systems still exist today in deep oceans, hot springs, and underground ecosystems, almost like biological echoes from another world. In fact, certain modern microorganisms may resemble some of Earth's oldest life strategies more closely than any large animal ever could. That continuity across billions of years feels almost eerie. While dinosaurs disappeared and civilizations rise and fall in brief geological moments, microscopic life continues, enduring through conditions that would destroy most complex organisms instantly. And deep beneath the storms of the ancient Earth, endurance mattered more than strength. The oceans were not peaceful refuges. Volcanic eruptions beneath the water could rapidly alter local chemistry. Asteroid impacts may have heated the seas dramatically during certain periods. Some scientists suspect entire oceans may have experienced cycles of warming and chemical disruption intense enough to wipe out huge populations of primitive organisms repeatedly. But microbial life recovers quickly when conditions stabilize, because evolution at that scale moves differently. Fast reproduction allows adaptation across vast numbers of generations in relatively short periods of time. That resilience may explain why life survived despite an Earth that often seemed determined to erase it. There is also another fascinating possibility connected to these early oceans. Some researchers think life may have emerged more than once. Not necessarily intelligent life or complex ecosystems, but primitive chemistry crossing into biological behavior multiple times independently before only certain lineages survived long term. If true, the ancient oceans were not simply the birthplace of one fragile chain of evolution. They may have been experimental environments where countless biological attempts appeared and vanished without leaving descendants. Most would have disappeared completely, erased by chemistry, competition, or planetary instability. The organisms alive today would simply be the survivors of a much larger, hidden history. We may never know if that idea is correct, but it changes how the oceans feel emotionally. Instead of a single, miraculous event, the origin of life becomes something more chaotic, more uncertain, almost like the planet repeatedly trying different possibilities until one endured. And all of this happened in a world where the surface sky may have meant almost nothing to the creatures below. That detail matters because humans instinctively associate life with sunlight. We imagine blue skies, green plants, warmth, and open landscapes. But the earliest ecosystems may have evolved without ever seeing the sun clearly at all. Deep underwater, beneath miles of mineral-rich ocean, life learned to survive using the Earth itself as an energy source. In some ways, the planet was feeding its first organisms directly through heat and chemistry rising from inside its own crust. That possibility becomes even more intriguing when scientists consider worlds beyond Earth. Moons like Europa and Enceladus contain subsurface oceans beneath thick layers of ice, and some researchers speculate hydrothermal activity could exist there too. If life on Earth truly began around deep ocean vents independent of sunlight, then perhaps similar environments elsewhere in the universe might also support biology hidden beneath dark oceans. Suddenly, Earth's ancient seas stop feeling like distant history and start feeling like a model for alien worlds. But even on Earth, these oceans remained incredibly isolated for unimaginable lengths of time. No forests broke the horizon above them. No animals crawled onto land. The continents themselves were smaller, unstable, and mostly barren rock. Waves crashed endlessly against black volcanic shorelines beneath thick clouds and constant storms. Yet beneath those waters, evolution was already moving quietly toward futures no organism could possibly predict. Every whale, every eagle, every human city, every tree, every dinosaur, every civilization traces back to life forms so small and simple they could drift unnoticed through a drop of ancient seawater. And perhaps the strangest part is that those first organisms survived not because the world became gentle, but because they adapted to a world that never was. By the time Earth entered the Carboniferous period, roughly 300 million years ago, the planet no longer looked like a barren world struggling to survive beneath endless storms. It had become something far stranger. Imagine standing at the edge of an ancient swamp, stretching farther than the eye can see, under a sky heavy with warm mist and dark clouds that almost never fully disappear. The air feels thick enough to drink. Every breath is damp, dense, and rich with oxygen far beyond modern levels. Towering forests rise from black, waterlogged ground. But these are not forests in the way humans understand them today. There are no birds singing in the canopy, no flowers, no grass, no familiar trees with broad branches spreading toward sunlight. Instead, giant club mosses rise like living pillars, their trunks covered in strange patterns resembling reptile scales. Massive horsetails grow in dense clusters taller than houses. Primitive ferns spread endlessly across the wetlands, forming green labyrinths above shallow, dark water that barely moves. Everything is wet. Everything is decaying. And everything is alive. This was one of the strangest ecosystems Earth ever created. A world where heat, moisture, and oxygen combined to produce life forms so bizarre that even modern rainforests seem tame by comparison. The Carboniferous forests existed because the planet itself had shifted into an unusually humid state. Vast, swampy lowlands covered enormous regions near the equator, especially across what would eventually become North America and Europe. Warm temperatures and constant rainfall fed explosive plant growth year after year without true dry seasons in many areas. Dead vegetation piled into thick layers faster than it could fully decompose, especially in oxygen-poor swamp waters. Over immense spans of time, those buried forests would slowly transform into the coal deposits that powered the Industrial Revolution hundreds of millions of years later. In a strange way, modern civilization still burns the remains of those lost wet forests every single day. But long before humans discovered coal, these swamps were already reshaping the atmosphere itself. Plants during the Carboniferous absorbed enormous amounts of carbon dioxide while releasing oxygen, and many scientists believe atmospheric oxygen levels rose significantly higher than today, perhaps reaching over 30% compared to the modern 21%. That difference may not sound dramatic at first, but it changed the entire logic of life on Earth. Fires could ignite more easily. Animals breathed differently, and insects reached sizes that now seem almost impossible. Dragonflies with wingspans over 2 feet hunted above the swamps like living aircraft. Giant millipede-like arthropods crawled across the wet forest floor at lengths exceeding 6 feet. Even the air itself may have contributed to the unsettling feeling of this world. With higher oxygen concentrations, dense humidity, rotting vegetation, and constant evaporation from endless wetlands, the atmosphere may have felt heavy, almost intoxicating. Every surface sweated with moisture. Fog drifted between trunks constantly. Sunlight rarely reached the swamp floor clearly because the forests trapped humidity beneath their towering canopies. Some paleontologists believe decomposition worked differently in these ancient ecosystems because fungi capable of efficiently breaking down lignin, one of the tough structural materials in plants, may not yet have evolved fully. If true, enormous amounts of dead wood accumulated instead of rotting quickly, helping create the vast coal-forming layers buried beneath modern continents. That possibility changes the emotional atmosphere of the Carboniferous world. These forests were not simply alive, they were piling up the remains of their own growth faster than the planet could recycle them. Imagine walking through a place where fallen trunks remain half submerged in black water for centuries, while new forests rise directly above older, dead ones. A world where decay never fully catches up to growth. In many ways, the Earth had become biologically overloaded, and that overload produced creatures unlike anything alive today. The giant insects of the Carboniferous are often treated almost like fantasy monsters in documentaries, but their existence reveals something deeper about how sensitive life is to atmospheric conditions. Insects breathe through tiny openings connected to tube-like structures rather than lungs, and higher oxygen concentrations may have allowed oxygen to diffuse through their bodies more efficiently, supporting larger sizes than modern conditions permit. That does not mean oxygen alone created giant insects. Climate, competition, and evolutionary pressures also mattered. But the important detail is that Earth itself had become physically different enough to change the possible scale of life. Sometimes evolution does not invent entirely new biological systems. Sometimes the environment simply relaxes the limits. Yet, despite the abundance of life, these forests were probably not peaceful places. Warm, stagnant water creates ideal conditions for parasites, fungal growth, rot, and disease. Many regions likely smelled strongly of decomposition mixed with wet vegetation and mineral-rich mud. Huge storms rolled across the swamps regularly, flattening sections of forest into flooded debris fields. Rivers shifted constantly through soft, saturated land, drowning entire ecosystems beneath sediment. And oxygen-rich atmospheres may have intensified wildfires during dry intervals, creating sudden destruction inside landscapes otherwise dominated by moisture. The Carboniferous world was balanced between water and fire in ways that feel almost contradictory. Wet enough to grow endless forests, oxygen-rich enough to burn explosively. That tension may explain why these ecosystems changed so dramatically over time. There is also something psychologically unsettling about the architecture of these forests themselves. Modern forests feel familiar because they are shaped by flowering plants, birds, mammals, and ecosystems humans evolved alongside. Carboniferous forests were structured differently. Many plants reproduced through spores rather than seeds. Trunks often rose tall, without broad branching canopies like modern trees. Dense layers of giant ferns and primitive vegetation blocked movement across the swamp floor. Enormous insects moved through the air with unfamiliar rhythms. Amphibian-like creatures lurked near black pools beneath curtains of mist. If a modern human entered this world, they might recognize it as biological, but not entirely terrestrial. It would feel closer to an alien planet than to modern Earth. And perhaps the strangest part is that vertebrate animals were still relatively small players inside these ecosystems. The forests themselves dominated everything. Plant life controlled the atmosphere, shaped the climate, altered the chemistry of the planet, and determined where animals could survive. In a sense, Earth during the Carboniferous was less an animal world than a machine for growing wet forests on a massive scale. Those forests influenced weather patterns directly. Through evaporation and transpiration, vast vegetation systems release enormous quantities of moisture into the atmosphere, even today. Imagine how powerful that process became across endless prehistoric swamps under warmer global conditions. Rain fed the forests, and the forests fed the rain in return, creating self-reinforcing cycles of humidity and growth. Some scientists suspect these ancient ecosystems may have significantly influenced regional climates through feedback loops similar to those observed in modern tropical rainforests. If true, then parts of the Carboniferous world were not merely enduring constant moisture, they were helping generate it. And yet, despite how unstoppable these forests appear, they were temporary. Earth never stays in one condition forever. Tectonic shifts slowly altered continents and ocean circulation. Climate patterns changed. Glacial cycles expanded in parts of the late Carboniferous and early Permian. Swamp ecosystems shrank or fragmented in many regions. Atmospheric oxygen eventually declined from its peak levels. The age of giant insects faded. Many ancient plant groups disappeared or lost dominance. Entire worlds that once seemed permanent vanished, slowly enough that no individual creature could possibly notice the transformation happening around them. That may be one of the quietest but most important truths hidden inside Earth's history. Extinction often does not arrive dramatically at first. Sometimes, worlds disappear through gradual environmental changes unfolding across millions of years. A forest does not realize it is the last version of itself, and perhaps that is why the Carboniferous feels strangely haunting compared to later prehistoric eras. Dinosaurs inspire awe because they were large and powerful, but these endless wet forests inspire something more unsettling. They reveal how profoundly the planet can reshape life when climate conditions remain stable long enough. Given enough warmth, enough rain, enough oxygen, and enough time, Earth can build ecosystems so unfamiliar that modern humans would struggle to believe they once truly existed. Even the coal beneath cities today is evidence of those vanished swamps. Every train powered during the Industrial Revolution, every early factory furnace, every steamship crossing the ocean was burning compressed sunlight captured by forests that grew under skies almost permanently wet, hundreds of millions of years before humans evolved. In a way, the ancient rain never completely ended. Its memory still burns beneath modern civilization. If you walked through the endless wet forests of the ancient Earth long enough, eventually you would begin noticing something unsettling hiding beneath the giant plants and dark swamp water. The forest was not only growing, it was being eaten alive from underneath. Every fallen trunk, every dead fern, every collapsed layer of vegetation slowly disappeared into a hidden biological network spreading through the soil, water, and rotting wood in silence. In a world where rain rarely stopped and humidity clung to every surface, fungi may have become some of the most powerful living things on the planet. Not because they were fast, not because they were violent, but because moisture gave them control over decay itself. Modern humans usually think of fungi as background life: mushrooms after rain, mold on old bread, strange growths hidden in dark corners. But on the ancient Earth, especially during long, humid eras, fungi may have shaped ecosystems almost as profoundly as forests themselves. In some environments, they may have controlled how quickly life died, how nutrients moved, how soils formed, and possibly even which organisms survived long enough to evolve further. The deeper scientists study fungal networks today, the stranger they appear. Beneath modern forests, fungi form enormous underground systems connecting plant roots across vast areas through microscopic threads called hyphae. Some researchers describe these systems almost like biological communication networks because they can transport nutrients and chemical signals between plants. Trees in modern forests sometimes survive not as isolated organisms, but as participants inside larger, interconnected systems heavily dependent on fungi. That relationship becomes even more important in a world drowning in constant moisture. Wet environments accelerate growth, but they also accelerate collapse. Dead material piles up quickly, especially in swamp ecosystems where oxygen levels fluctuate and decomposition becomes complicated. Without organisms capable of recycling that dead matter, entire landscapes could choke beneath their own remains. Fungi solved that problem better than almost anything else on Earth. They evolved extraordinary abilities to break apart tough biological materials like lignin and cellulose, substances that give plants their structure and durability. In many ways, fungi unlocked the stored energy inside forests, and once they did, the balance of the planet began changing. But there is another reason fungi feel so perfectly adapted to a world of endless rain. Unlike animals, fungi do not need to hunt actively or move through landscapes searching for food. Moisture itself allows them to spread. Damp air carries spores through forests invisibly. Wet soil protects delicate fungal threads from drying out. Rotting wood becomes a permanent feeding ground. Rain does not interrupt fungal life. It helps distribute it. In a prehistoric world dominated by swamps, fog, and constant humidity, fungal growth may have spread almost everywhere organic material existed. Entire fallen forests could become feeding grounds beneath layers of mist and darkness. And some of the organisms living during these periods may have reached sizes difficult to imagine today. One of the strangest examples is a mysterious fossil organism called Prototaxites, which lived hundreds of millions of years before dinosaurs appeared. For decades, scientists argued fiercely over what Prototaxites actually was. Some believed it was an ancient tree. Others thought it might be algae or some entirely unknown form of life. But many researchers now suspect it was a gigantic fungus or fungus-like organism. potentially growing over 20 feet tall in some cases. Imagine that image carefully. Before trees dominated the earth, towering fungal structures may have risen from damp, prehistoric landscapes beneath gray skies and endless rain. Not forests of wood, but forests of living decay. Even today, scientists continue debating exactly how prototaxites lived and whether all specimens belonged to the same type of organism. But its existence hints at how different early terrestrial ecosystems truly were. There may have been periods when fungi were not hidden beneath forests. They were the forests. That possibility becomes even more fascinating when considering how hostile early land environments once were. Before soils fully developed and before large animals spread across continents, fungi may have helped prepare the land itself for future ecosystems. Some scientists think fungi formed partnerships with primitive plants extremely early in terrestrial evolution, helping them absorb nutrients from barren rock and survive outside aquatic environments. Without fungal relationships, plants may have struggled to colonize land effectively at all. In that sense, forests may have grown on Earth not independently, but alongside hidden fungal systems operating beneath them from the beginning. The planet's surface was not conquered by plants alone. It was transformed through biological alliances invisible to the eye, and moisture made those alliances stronger. Rain softens wood. Rain feeds rot. Rain turns fallen vegetation into dark organic soil rich with nutrients. In constantly wet ecosystems, death does not disappear cleanly. It lingers. It sinks into the ground slowly. Black water fills hollow trunks, while fungal growth spreads through the interior like veins. Some modern rainforests already hint at this ancient process. In tropical environments today, fallen trees can vanish surprisingly fast beneath insects, fungi, bacteria, and moisture. But ancient swamp worlds may have amplified that process to extraordinary levels. The air itself likely carried the smell of decomposition constantly. Warm humidity mixed with spores, decaying vegetation, stagnant water, and wet soil into an atmosphere humans would probably find overwhelming. And yet, those conditions created astonishing biological productivity. That is one of the strange contradictions hidden inside Earth's history. Rot and growth are not opposites, they are partners. The more life expands, the more death accumulates beneath it, and fungi sit directly at the center of that exchange. They convert collapse into continuity. They turn dead forests into future forests. In a world where rain never truly ends, that role becomes almost godlike from an ecological perspective. But fungi are not only decomposers, they are survivors. Some modern fungi can tolerate extreme radiation, freezing conditions, deep ocean pressure, toxic environments, and long periods of dormancy. Certain fungal spores can remain inactive for remarkable lengths of time before moisture awakens them again. That resilience may explain why fungi spread so effectively throughout Earth's history whenever wet climates expanded. In many extinction events, fungal activity may even have increased afterward as dead ecosystems collapsed across enormous regions. There is a controversial hypothesis, sometimes called the fungal spike idea, connected to the aftermath of the asteroid impact that ended the age of non-avian dinosaurs. Some scientists have proposed that fungal populations surged globally due to massive amounts of decaying organic matter after the catastrophe. The evidence remains debated, and researchers do not fully agree on how significant this effect truly was. But the idea itself reveals something important about fungi. They thrive when worlds fall apart. In stable ecosystems, they remain hidden beneath the surface. In dying ecosystems, they rise. That pattern makes them feel strangely timeless compared to many animals. Mammals dominate certain eras. Reptiles dominate others. But fungi persist quietly through almost all of them. Perhaps because fungi do not depend on controlling environments the way large animals often do. They adapt to instability itself. And in a permanently wet world, instability is constant. Storms flatten forests. Floods drown ecosystems. Heat accelerates decay. Yet fungal networks continue spreading through the darkness beneath everything else. There is also a deeper psychological reason fungi feel unsettling to humans. Animals consume living things directly. Fungi consume what is already collapsing. They appear where life softens. Mold spreads across abandoned structures. Mushrooms emerge from dead wood after rain. Rot blooms silently in darkness. Fungi remind humans that nature does not waste death. In prehistoric, rain-soaked forests, that reality would have been impossible to ignore. Every fallen trunk immediately became part of another living system waiting below the surface. Entire landscapes were recycling themselves continuously. And perhaps the strangest part is how invisible most of this process remained. Even today, the mushroom people see above ground is usually only a small reproductive structure. The true organism often exists underground, hidden in enormous branching networks extending far beyond visible surfaces. Some modern fungal organisms rank among the largest living entities on Earth by area. That means ancient wet ecosystems may have contained biological systems far larger and older than anything moving visibly through the forests above them. Creatures walked across fungal kingdoms without ever realizing it. In a world of endless rain, hidden life may have mattered more than visible life. That idea changes how prehistoric Earth feels emotionally. The giant insects, towering swamp forests, and strange amphibians capture attention first, but beneath all of them existed something quieter and possibly more important. A hidden system breaking down death, redistributing nutrients, feeding new growth, and binding ecosystems together through moisture and decay. Without fungi, the wet ancient world may have collapsed beneath its own dead matter. Instead, the rain fed an endless cycle where forests died slowly into darkness and rose again from the remains. And somewhere inside those dim prehistoric swamps, beneath black clouds and drifting fog, life may have learned one of its oldest lessons. Survival is not only about resisting decay. Sometimes survival depends on becoming part of it. For most of Earth's early history, life stayed close to water, as if the planet itself was warning everything alive not to wander too far from the oceans that created it. And in many ways, that warning made sense. The ancient world beyond the shoreline was harsh, unstable, and strangely empty. There were no forests offering shade, no deep soils rich with nutrients, no grasslands, no birds overhead, and no large animals moving across the land. The continents were raw, wet, and exposed beneath enormous skies filled with shifting clouds and heavy rain. Rivers cut through barren stone. Mudflats stretched endlessly beneath mist. The edges of shallow seas flooded constantly with changing tides, storms, and seasonal surges of water. Yet somewhere within these unstable borderlands between ocean and land, a quiet evolutionary gamble began unfolding. Certain creatures started surviving just long enough outside the water to discover that the empty world above held opportunities almost no competition had reached yet. The strange thing is that the first major step onto land may not have looked dramatic at all. It probably did not happen because a fish suddenly decided to conquer the earth. More likely, it happened through countless tiny advantages accumulating slowly over millions of years. Shallow coastal waters during the late Devonian period were often dangerous places. Oxygen levels in stagnant pools could drop sharply. Drought-like conditions may have trapped fish in shrinking wetlands. Predators filled many aquatic ecosystems. In some environments, being able to push through mud, survive brief exposure to air, or move between isolated pools could mean the difference between reproduction and extinction. Evolution rarely plans ahead. It modifies survival strategies that already work slightly better than alternatives. Some ancient fish gradually developed stronger fins, capable of supporting weight in shallow environments. Others evolved primitive lungs or air-breathing adaptations alongside gills. Fossils of creatures like Tiktaalik reveal combinations of fish and tetrapod features so unusual that they seem almost suspended between worlds. It had scales and fins, but also a flexible neck and limb-like structures strong enough to support movement in shallow water or muddy terrain. It was not fully terrestrial, but it no longer belonged entirely to the water either. That transitional state may have defined life on land for a very long time. Modern humans often imagine the first land animals marching confidently onto dry continents, but the reality was probably much messier. Early tetrapods likely stayed close to wetlands, swamps, river systems, and humid environments where moisture protected their bodies from drying out. Their skin was vulnerable. Their eggs still depended heavily on water. Their movement on land was awkward and exhausting compared to swimming. In a sense, the first animals on land were not escaping the water. They were carrying pieces of the water with them. And the climate of the ancient Earth may have made that transition possible. Warm temperatures and widespread humidity reduced the risk of dehydration. Constant rainfall created enormous swamp systems where shallow pools, mudflats, flooded forests, and river deltas blurred together into giant transitional habitats. There were countless places where water and land mixed imperfectly. Those environments acted almost like evolutionary training grounds. Creatures did not need to survive in dry deserts or open plains yet, because those ecosystems barely existed in recognizable forms. Instead, life moved gradually through landscapes where the ground itself often remained soaked beneath heavy moisture and constant rain. Imagine standing inside one of these prehistoric wetlands roughly 370 million years ago. The air is warm and thick with fog drifting across shallow black water. Primitive plants rise from muddy banks, while giant arthropods crawl through damp vegetation nearby. The sounds are unfamiliar. Splashing water, distant thunder, insects moving through wet growth. Somewhere near the shoreline, a creature, half fish and half amphibian, drags itself through thick mud using muscular fins that are slowly becoming limbs. Every movement looks inefficient. The body strains awkwardly against gravity. On land, breathing changes, vision changes, sound changes. Even the simple act of supporting body weight becomes a completely new challenge. Water had always carried much of life's physical burden before this moment. Now, organisms had to survive inside an environment where their own bodies suddenly felt heavy. That transition reshaped anatomy in extraordinary ways. Stronger limb bones evolved. Spines changed to support weight differently. Ribs expanded to help breathing outside water. Heads became more mobile. Sensory systems adapted to new environments where vibrations traveled through air instead of water. In many cases, evolution reused old structures rather than inventing entirely new ones from scratch. Fish fins gradually transformed into limbs over immense spans of time because slight modifications kept improving survival in shallow environments generation after generation. But stepping onto land also introduced dangers unlike anything marine life had faced before. Ultraviolet radiation from sunlight became more intense outside the protection of water. Temperatures fluctuated more dramatically. Bodies dried out faster. Gravity strained muscles and skeletons constantly. Storms could flood habitats suddenly, while shifting wetlands might isolate populations completely. Some early tetrapods probably died within minutes if trapped too far from water. Others may have survived only because humid climates prevented rapid dehydration. In that sense, the ancient rainy world acted less like an obstacle and more like a protective bridge between aquatic and terrestrial life. Without widespread moisture, the first steps onto land may have been far more difficult. Rain softened the transition. Wet environments allowed evolution to experiment slowly. And while these early creatures struggled across muddy shorelines, the land itself was changing too. Plants had already begun spreading across continents before large animals fully arrived. Primitive forests and dense wet vegetation altered erosion patterns, stabilized soils, and increased organic matter in the environment. Rivers changed shape as plant roots held sediment together more effectively. Oxygen levels rose. Atmospheric chemistry shifted. The Earth that early tetrapods encountered was not barren anymore. It was becoming biologically engineered by plants and microbial systems into something more survivable. In many ways, animals colonized land only after other organisms prepared it first. There is something almost humbling about that sequence. Large animals tend to dominate human imagination, yet Earth's greatest transformations often begin invisibly through plants, fungi, microbes, and climate systems operating quietly over millions of years. The first vertebrates stepping onto land were entering ecosystems already shaped by forces far older and more stable than themselves, and they did not immediately become rulers there. For a long time, terrestrial environments remained dangerous experimental zones where survival depended on flexibility rather than dominance. Some scientists suspect certain early tetrapods spent most of their lives in water, despite possessing limbs capable of movement on land. Fossil evidence often suggests transitional lifestyles instead of fully terrestrial behavior. That ambiguity matters because evolution rarely moves in clean, straight lines. Some lineages adapted further to life on land. Others returned to aquatic environments. Many vanished completely. The fossil record preserves only fragments of a far more complicated biological story. Yet even with those uncertainties, one pattern remains clear. The movement onto land was not a single event. It was a prolonged ecological migration unfolding across millions of years, and moisture remained central to nearly every stage of it. Amphibian-like creatures flourished in humid ecosystems because their reproduction still depended heavily on water. Eggs lacking protective shells dried out easily. Larval stages often remained aquatic. Skin absorbed moisture directly from the environment. In permanently wet forests and swamp systems, these limitations mattered less. Rain-filled landscapes acted almost like extensions of the ancient seas, allowing vertebrate life to spread farther across continents without fully abandoning its aquatic origins. But eventually, evolution pushed further. One of the most important developments in terrestrial history was the evolution of the amniotic egg, which protected embryos within specialized membranes and reduced dependence on standing water for reproduction. This innovation allowed certain lineages to move deeper into drier environments and ultimately gave rise to reptiles, mammals, and eventually humans. Yet before that breakthrough, the first land animals survived largely because the world itself remained wet enough to forgive their weaknesses. That detail changes how the story feels emotionally. The conquest of land was not a bold invasion of a hostile frontier. It was more like life cautiously testing the edges of a rainy world that still resembled water in countless hidden ways. Even the soil remained saturated. Rivers overflowed constantly. Storm systems reshaped habitats without warning. Wet forests trapped humidity beneath dense vegetation. The line between land and water stayed unstable for millions of years. And perhaps that instability was exactly what evolution needed. Because stable worlds reward specialization, but unstable worlds reward adaptation. The first terrestrial animals were not perfect creatures designed for land. They were transitional survivors evolving inside uncertainty itself. Somewhere in those endless wetlands beneath dark, prehistoric skies, life learned that survival did not require certainty. It only required staying alive long enough for the next adaptation to appear. When most people imagine the age of dinosaurs, they picture dry, prehistoric plains beneath clear blue skies, giant reptiles walking through open valleys while volcanoes smoke quietly in the distance. But much of the dinosaur world may have felt far wetter, darker, and more unstable than those familiar images suggest. During large portions of the Mesozoic era, especially throughout parts of the Jurassic and Cretaceous periods, Earth operated as an enormous greenhouse planet. Global temperatures were significantly warmer than today. Polar ice was limited or possibly absent during certain intervals. Sea levels stood much higher, and atmospheric moisture circulated through the planet on a massive scale. Warm worlds hold more water in the air, And when enough heat and water combine over millions of years, storms stop feeling temporary. They become part of the architecture of the planet itself. Imagine standing inside a Cretaceous forest somewhere near what is now North Africa, nearly 95 million years ago. The air is heavy with humidity before dawn even arrives. Thick clouds move slowly above giant conifers and dense, fern-covered ground, while distant thunder rolls continuously beyond the horizon. Rivers overflow into floodplains so often that the land itself seems unable to decide whether it belongs to the forest or the water. Enormous insects buzz through wet heat beneath towering vegetation, while strange calls echo through the fog. Somewhere in the darkness, a predator moves through the mud almost silently, despite weighing several tons. In places like this, dinosaurs were not surviving occasional storms. They were living inside weather systems that shaped every part of their existence. Geological evidence suggests many dinosaur ecosystems experienced strong seasonal rainfall, monsoon-like climates, or extended humid conditions depending on geography and time period. Vast inland seas altered atmospheric circulation. Warm oceans fueled evaporation. Dense vegetation recycled moisture back into the air. Some regions likely experienced torrential rainfall, capable of transforming landscapes rapidly through flooding, erosion, and shifting river systems. In modern tropical environments, heavy storms already reshape forests constantly. Now, imagine those same forces operating across a planet hotter than modern Earth and populated by ecosystems unlike anything alive today. The dinosaur world may have been one of the stormiest periods in Earth's history, and unlike mammals, dinosaurs often grew to sizes that made environmental instability especially dangerous. A small animal can hide from weather. A 40-ton sauropod cannot. Massive herbivores depended on huge quantities of vegetation and water every single day. That meant many species probably followed seasonal migration routes linked directly to rainfall patterns, river systems, and plant growth cycles. Fossil evidence from some dinosaur trackways suggests certain herds moved across enormous distances, possibly responding to environmental changes much like modern elephants or wildebeest. But in a prehistoric greenhouse climate, those migrations may have been even more unpredictable. A floodplain thriving one year could become a drowned swamp or dried mud basin after shifting rainfall patterns altered the region. Dinosaurs were not living in static environments frozen in time. They were surviving inside ecosystems constantly rearranged by water. Some of the most fascinating evidence for this comes from ancient river deposits and fossilized floodplain sediments found across the world. Many dinosaur fossils are preserved in layers suggesting catastrophic floods, sudden burial events, or rapidly shifting waterways. Entire forests could vanish beneath sediment after violent storms overwhelmed river systems. Young dinosaurs may have drowned during seasonal floods. Nests could be destroyed overnight by rising water levels. In fact, some paleontologists suspect nesting behavior itself evolved partly around environmental instability. Certain dinosaurs appear to have nested in colonies, perhaps increasing the odds that at least some offspring survived unpredictable conditions. Others may have chosen elevated ground or specific seasonal windows to avoid flooding. But even these strategies could fail when storms became too extreme. There is something strangely fragile about dinosaur eggs when viewed this way. We often think of dinosaurs as symbols of power, yet their young began life inside thin-shelled eggs, vulnerable to temperature changes, moisture fluctuations, predators, fungal growth, and flooding. In humid prehistoric environments, maintaining stable nesting conditions would have been difficult. Too much rain could suffocate embryos. Too little moisture could dry developing eggs. Some species may have buried eggs beneath vegetation or sediment to regulate humidity and heat naturally, similar to certain modern reptiles and birds. Others may have relied on microbial decomposition from wet plant material to warm nests indirectly. The more scientists study dinosaur reproduction, the more complex and environmentally sensitive it appears. And while storms threatened survival constantly, they also sustained the ecosystems dinosaurs depended on. Rain-fed forests dense enough to support enormous herbivores. Floodplains created fertile regions where vegetation regenerated rapidly. Wet climates expanded habitats for amphibians, fish, insects, and smaller prey species, supporting entire food webs. In many areas, constant moisture turned landscapes into biological engines, producing astonishing amounts of life. But biological abundance always carries hidden costs. Wet heat accelerates decay. Parasites thrive in humid environments. Fungal infections spread more easily. Standing water becomes dangerous. Even today, tropical ecosystems contain some of the highest biodiversity on Earth, alongside intense disease pressure and environmental competition. Dinosaur ecosystems likely operated similarly, perhaps even more intensely due to warmer global temperatures and widespread wetlands. Imagine the physical reality of living in those conditions. Thick mud trapping massive feet after heavy rain. Swarms of insects breeding near stagnant pools. Rotting vegetation releasing heavy organic smells into humid air. Thunderstorms arriving with little warning across open floodplains. Young animals separated from herds during sudden floods. Predators learning migration routes shaped by seasonal water movement. Entire ecosystems tied directly to the behavior of rain. In places like prehistoric North Africa, where giant predators such as Spinosaurus lived near vast river systems, wet conditions may have dominated daily life almost completely. Some scientists believe these environments supported immense fish populations, alongside crocodilian reptiles, turtles, and aquatic prey. Spinosaurus itself appears increasingly adapted for semi-aquatic behavior, suggesting certain large predators evolved specifically to exploit water-rich ecosystems. That detail changes the emotional atmosphere of the dinosaur age again. Instead of dry reptilian kingdoms, many regions may have resembled endless, storm-fed wetlands filled with giant animals adapted to mud, rivers, marshes, and unstable coastlines. And yet, despite how dominant dinosaurs became, they remained vulnerable to climate shifts happening over geological timescales. Changes in rainfall patterns could alter vegetation distribution dramatically. Sea level fluctuations reshaped coastlines and habitats repeatedly throughout the Mesozoic. Some extinction events during the dinosaur era may have involved environmental instability linked partly to changing climates rather than single, sudden disasters alone. Scientists continue debating the exact causes behind various prehistoric turnovers, but one pattern appears repeatedly throughout Earth's history. Ecosystems built around stable moisture systems become extremely sensitive when those systems change. Too much rain can destroy a world just as effectively as drought. There is also evidence suggesting some dinosaur regions experienced strong seasonal contrasts despite generally warm climates. Monsoon systems may have created cycles of flooding followed by dry periods, severe enough to concentrate animals around shrinking water sources. Fossil bone beds containing large numbers of individuals sometimes hint at mass deaths during environmental stress events. In these moments, even giant dinosaurs could become trapped by mud, starvation, dehydration, or collapsing ecosystems. Size created advantages, but it also created dependence. Large animals require stable environments to survive long term, and the Mesozoic Earth, despite its biological richness, may have been far less stable than it first appears. Even the forests themselves were changing continuously. Flowering plants emerged and spread during the Cretaceous, transforming ecosystems in ways scientists still study today. New plant groups altered food sources, insect relationships, forest structure, and possibly even atmospheric chemistry over time. Dinosaurs were not simply walking through static prehistoric scenery. They were living during one of the most dynamic ecological periods in Earth's history. Storms, heat, changing vegetation, shifting rivers, volcanic activity, rising seas, all of it formed the background of daily survival. And somewhere inside those endless humid landscapes, life adapted again and again to conditions humans would likely find exhausting and overwhelming. Perhaps that is why the age of dinosaurs feels so strange emotionally when viewed through climate instead of skeletons. It stops looking like a world of monsters and starts looking like a world ruled by environmental pressure. Dinosaurs were not surviving because nature was gentle to them. They survived because evolution kept shaping them fast enough to keep pace with a planet drowning in heat, moisture, and constant change. Even the largest creatures to ever walk the earth still had to endure the rain. If rain falls long enough, the sky itself begins to change. Not just emotionally, not just visually, but physically. Clouds stop feeling temporary. Light changes. Temperatures shift. Entire ecosystems evolve beneath a ceiling of moisture so constant that the boundary between atmosphere and ocean starts to feel strangely blurred. And over millions of years, the sky above the ancient Earth may have become one of the most important forces shaping the evolution of life below it. Modern humans are deeply accustomed to variation in the sky. Clear mornings, blue afternoons, dry seasons, sunlight breaking through clouds after storms. We instinctively treat brightness as normal and darkness as temporary. But there were periods in Earth's history when many regions of the planet may have spent enormous stretches of time beneath thick cloud systems, warm atmospheric haze, heavy humidity, and recurring storms powerful enough to dominate entire continents. In those worlds, sunlight still existed, but it often arrived filtered, muted, diffused through layers of vapor and cloud before touching the surface. The Earth may not have looked bright even during daytime. Imagine standing inside a prehistoric rainforest during one of these humid greenhouse eras. The sky above is technically daylit, but the light barely reaches the ground clearly. Massive trees trap moisture beneath their canopies, while fog hangs between trunks even at noon. Rain falls lightly for hours, then suddenly intensifies into violent downpours before fading back into mist again. The air itself feels dim. Colors become darker, softer, almost drowned beneath moisture. Every sound carries differently in the wet atmosphere. Thunder rolls across enormous distances. Water drips constantly from leaves. The horizon disappears behind curtains of rain and vapor. And beyond the forest canopy, gigantic cloud systems continue building heat and moisture above oceans warmer than much of the modern world. Climate scientists understand today that warm atmospheres hold more water vapor. That relationship matters enormously because water vapor itself is a greenhouse gas. The warmer Earth becomes, the more moisture enters the atmosphere. And the more moisture enters the atmosphere, the more heat can become trapped. This creates feedback loops capable of reshaping weather systems on planetary scales. During certain periods of Earth's deep past, especially in major greenhouse climates like parts of the Mesozoic era, global temperatures were significantly higher than today. Sea levels rose, polar ice diminished, evaporation intensified. Storm systems likely carried far more moisture than modern equivalents in many regions. Some scientists suspect certain prehistoric climates may have supported extremely active hydrological cycles where evaporation and rainfall operated almost continuously across huge portions of the planet. In those conditions, the sky itself becomes part of the ecosystem rather than merely background scenery. But there is another consequence humans rarely think about when imagining endless rain. Darkness changes evolution. Not complete darkness like deep oceans or caves, but persistent low-light environments where visibility remains limited beneath clouds, fog, forests, and storms. Modern rainforests already reveal hints of this effect. Dense vegetation combined with constant moisture reduces direct sunlight dramatically near the forest floor. Animals living there often rely heavily on sound, smell, vibration, movement, and environmental awareness rather than long-distance vision alone. Now imagine similar conditions operating for millions upon millions of years across giant prehistoric ecosystems. Some species may have evolved sensory systems shaped not by open sunlight, but by filtered worlds where visibility remained uncertain most of the time. Certain dinosaurs developed enormous eye sockets, possibly suited for low-light activity, though scientists still debate aspects of their behavior. Some prehistoric amphibians and reptiles may have relied heavily on vibration sensing near waterlogged environments where sight became unreliable during storms. Insects adapted to humid forest systems likely navigated through chemical signals, moisture gradients, and sound as much as vision. Evolution responds to available information, and in worlds dominated by rain, the atmosphere itself limits what information travels clearly. Sound behaves differently in humid air. Smell lingers longer. Visibility shrinks. The world becomes closer, heavier, more immediate. Even the sky's color may have looked different during certain periods of Earth's history. Atmospheric composition changed dramatically across geological time. Oxygen, carbon dioxide, methane, volcanic aerosols, dust, water vapor, all fluctuated depending on biological activity, tectonic forces, volcanic eruptions, and climate conditions. During some ancient eras, haze and airborne particles may have tinted sunlight in unusual ways. Massive volcanic events could darken skies temporarily on continental scales. Wildfire smoke may have mixed with humid atmospheres during oxygen-rich periods. Warm oceans released huge quantities of moisture continuously into the air. Some scientists studying Earth's ancient climates suggest certain greenhouse periods may have resembled modern tropical systems expanded across much larger portions of the globe. That does not necessarily mean non-stop rain everywhere all the time, but it does imply environments where clouds, storms, humidity, and heavy atmospheric moisture became dominant features of daily life across enormous regions. There is also a psychological dimension to these skies that humans instinctively understand even without scientific training. Long periods without sunlight affect behavior. Modern studies show reduced sunlight exposure can influence sleep cycles, hormones, mood, and mental health in humans. While prehistoric animals were obviously adapted to their own environments, persistent dimness still changes how ecosystems function. Predators hunt differently in low visibility. Migration patterns shift. Reproduction cycles may respond to changing seasonal light conditions. Forest growth changes depending on cloud cover and rainfall intensity. The atmosphere is not separate from biology. It shapes biology constantly. And perhaps the strangest possibility is that Earth's ancient skies may have appeared frighteningly alive compared to modern ones. Today, humans can watch storms move across satellites and radar maps, understanding them as weather systems governed by atmospheric physics. But on the ancient Earth, storms may have reached scales difficult for modern civilization to fully imagine. With warmer oceans fueling evaporation and fewer modern geographic barriers in certain eras, gigantic storm systems could potentially grow with enormous energy reserves. Hurricanes today already demonstrate the terrifying power stored in warm ocean water. Increase global warmth significantly over geological timescales, and the atmosphere itself begins carrying far more energy and moisture than modern humans are used to experiencing. Ancient storms may have flooded entire ecosystems repeatedly, while reshaping coastlines and river systems generation after generation. Some paleoclimate models suggest prehistoric rainfall events in certain greenhouse periods could have been extraordinarily intense. Sedimentary evidence from ancient flood deposits supports the idea that massive storm-driven flooding occurred regularly in parts of the prehistoric world. Rivers changed course violently. Wetlands expanded and vanished. Forests drowned beneath sediment. Entire regions may have spent centuries trapped between flood and evaporation cycles. Yet life adapted anyway. That may be the most important pattern hidden inside these ancient skies. Organisms did not evolve despite unstable weather. They evolved inside it. And perhaps the atmosphere itself influenced evolutionary speed more than humans usually realize. Stable climates often support highly specialized ecosystems. Unstable climates reward flexibility. When storms constantly reshape habitats, creatures capable of adapting quickly gain advantages over those dependent on narrow environmental conditions. Some extinction events throughout Earth's history may even connect partly to disruptions in atmospheric systems rather than simple temperature changes alone. Shifts in rainfall patterns can collapse forests, alter ocean circulation, destroy food chains, and trigger cascading ecological failures even without dramatic changes in average global temperature. Water distribution matters as much as heat. In a world where rain defines survival, changing the sky means changing life itself. There is another fascinating possibility tied to these ancient atmospheric conditions. Some scientists studying exoplanets believe certain distant worlds may exist in permanent storm states due to extreme greenhouse conditions, tidal locking, or dense atmospheres rich in water vapor. Earth's own prehistoric greenhouse eras may offer partial clues about how such planets function. That realization makes ancient Earth feel less like distant history and more like a bridge between familiar modern environments and entirely alien worlds. The skies above prehistoric forests may have looked closer to science fiction than modern weather forecasts. Thick clouds rolling endlessly above giant swamps, constant thunder beyond the horizon, humid air glowing dimly beneath filtered sunlight, rain moving across ecosystems already saturated beyond imagination, and underneath it all, evolution continuing patiently through instability. Perhaps that is why endless rain changes the emotional feeling of a planet so deeply. Rain softens boundaries. It blurs distance. It hides horizons. Under constant storms, the world feels smaller and larger at the same time. Forests become labyrinths. Rivers become temporary oceans. The sky stops feeling empty and starts feeling heavy, almost physical. Life beneath those skies evolves differently because perception itself changes. Creatures survive by sensing pressure, movement, moisture, sound, vibration, scent, and timing, rather than relying purely on sight. In some ancient worlds, the atmosphere may have trained evolution to trust uncertainty. And maybe that is the strangest part of all. The sky humans know today, bright, open, blue, predictable, may actually be one of the calmer versions Earth has ever worn. When people imagine mass extinctions, they usually picture something sudden and violent. A giant asteroid tearing across the sky, a volcanic apocalypse turning day into night, a single catastrophic moment dividing one world from another. But some of the deadliest extinction events in Earth's history may not have arrived as one dramatic impact at all. Some may have unfolded through changes so vast, slow, and relentless that entire ecosystems collapsed without ever fully understanding what was happening to them. And again, hidden beneath those collapses, water and climate appear at the center of the story. Not only fire, not only explosions, but rain, oceans, humidity, temperature, and the sky itself slowly shifting out of balance. The strange thing about water is that life depends on it so completely that even slight changes in how it moves through the planet can become catastrophic over geological time. Too little rain destroys forests. Too much rain strips nutrients from ecosystems and floods entire continents. Warm oceans hold less oxygen. Cold oceans alter circulation patterns. Rising seas erase coastlines. Falling seas destroy shallow marine habitats where enormous amounts of life exist. Water creates ecosystems, but it also controls how quickly they can disappear. And Earth's history is filled with moments when the planet's climate systems changed so dramatically that life could not adapt fast enough. One of the most haunting examples happened around 252 million years ago, during the end Permian extinction, often called the Great Dying. It remains the most severe mass extinction known in Earth's history. An estimated majority of marine species vanished, alongside massive losses on land. Entire ecosystems collapsed across the planet. Forests disappeared. Oceans changed chemically. Food chains shattered. And while scientists continue debating details of exactly how events unfolded, enormous volcanic eruptions in what is now Siberia appear to have played a major role. These eruptions, known as the Siberian traps, released astonishing quantities of carbon dioxide and other gases into the atmosphere over immense periods of time. The climate began warming dramatically. Oceans absorbed heat. Atmospheric chemistry changed. Rain itself may have turned acidic in many regions due to sulfur-rich emissions interacting with moisture in the air. Imagine standing in that world as the sky slowly becomes poisonous. Forests, weakened by heat, begin dying across enormous distances. Rivers carry ash and nutrients into oceans, already struggling under rising temperatures. Warm water holds less oxygen, and eventually, vast marine regions begin suffocating. Scientists refer to some of these areas as anoxic zones, places where oxygen levels drop so low that many organisms cannot survive. Evidence suggests ancient oceans during the end Permian crisis may have developed widespread oxygen depletion severe enough to devastate marine ecosystems globally. The water itself became deadly, and unlike a sudden asteroid strike, this destruction may have unfolded across thousands or tens of thousands of years, long enough for generations of creatures to continue reproducing inside collapsing systems they could not understand. Some scientists suspect microbial blooms may have worsened conditions further. As ecosystems destabilized, bacteria producing toxic hydrogen sulfide could have expanded in oxygen-poor waters. Hydrogen sulfide is deadly to many organisms and may even have entered parts of the atmosphere under extreme conditions. Certain geological evidence hints at deeply disturbed ocean chemistry during this time, though researchers continue debating the exact scale and mechanisms involved. Still, the overall picture remains terrifying. Earth did not simply become hotter. The planet's interconnected water systems began failing together. Oceans warmed, oxygen dropped, rain chemistry changed, weather patterns shifted, forests collapsed, and once enough ecological links broke simultaneously, recovery became incredibly difficult. The Great Dying reveals something profoundly unsettling about climate-driven extinctions. Life does not need direct violence to disappear. It only needs the systems supporting it to become unstable long enough. Water amplifies that instability because it connects everything. Oceans regulate temperature. Clouds control rainfall. Rivers transport nutrients. Ice reflects sunlight. Atmospheric moisture influences storms. Disturb one part of the hydrological system strongly enough, and consequences begin spreading outward across the entire planet. Similar patterns appear in other extinction events too. During parts of the late Devonian extinction, roughly 370 million years ago, marine ecosystems suffered repeated crises, possibly connected to changing climate conditions, ocean oxygen loss, and disruptions in nutrient cycles. Scientists still debate exact causes because the extinction unfolded in pulses over millions of years rather than through one obvious catastrophe. Some hypotheses involve expanding plant life, altering weathering and nutrient runoff into oceans, potentially triggering algal blooms and oxygen depletion in marine environments. Others point toward volcanic activity, climate cooling, or sea level changes. The uncertainty itself is revealing. Earth's systems are so interconnected that multiple environmental stresses can combine into extinctions difficult to reduce to one simple explanation. And often, water sits at the center of those interactions. Even extinction events strongly associated with impacts may have involved climate and hydrological collapse afterward. The asteroid that ended the age of non-avian dinosaurs certainly caused immediate devastation, but the long-term environmental consequences likely mattered just as much. Dust and aerosols blocked sunlight, temperatures shifted dramatically, photosynthesis collapsed in many ecosystems. Acid rain may have fallen across huge regions as atmospheric chemistry changed. Food chains dependent on stable climates and plant growth broke apart. Oceans acidified. Marine ecosystems destabilized. In a sense, the asteroid was not simply a collision. It was a trigger that disrupted the planet's atmospheric and water systems faster than many organisms could survive. There is also growing evidence that some prehistoric climates experienced extreme warming episodes known as hyperthermals, periods where global temperatures rose rapidly relative to geological norms. One famous example is the Paleocene-Eocene thermal maximum around 56 million years ago. During this event, huge amounts of carbon entered the atmosphere and oceans over a geologically short period. Temperatures increased significantly. Ocean chemistry changed. Some marine organisms experienced major extinction pressures. Tropical conditions expanded into higher latitudes. Rainfall patterns shifted dramatically in certain regions. Although this event was not as catastrophic as the Great Dying, it reveals how sensitive Earth's systems remain to carbon-driven warming and hydrological disruption. Warm atmospheres intensify evaporation. Intensified evaporation alters storms and rainfall. Oceans absorb both heat and carbon. Climate and water become inseparable. And perhaps the most disturbing part is how invisible these transformations can appear at first. Extinction often begins quietly. A river changes course. A breeding season shifts. Rain arrives too heavily or not heavily enough. Forests weaken slowly under heat stress. Coral reefs bleach. Wetlands disappear. Oxygen levels fluctuate in coastal waters. Species move toward cooler regions. Food chains become fragile. None of these changes look apocalyptic individually, but ecosystems survive through interconnected stability. Once enough small failures accumulate together, collapse accelerates suddenly. Fossil records sometimes preserve this eerie pattern. Species remain common for long periods, then vanish abruptly from geological layers once environmental thresholds are crossed. The Earth does not always warn life dramatically before changing the rules. Water also carries memory through the planet. Ice cores, ocean sediments, fossil shells, and ancient rock formations preserve evidence of rainfall, temperature, atmospheric chemistry, and sea level changes across unimaginable spans of time. Scientists reconstruct prehistoric climates partly by reading these watery archives hidden inside stone and ice. And again, those records show a planet constantly shifting between wetter and drier states, warmer and colder intervals, stable periods, and violent transitions. Earth's climate history is not a straight line toward balance. It is a story of repeated instability, interrupted by temporary equilibrium. There is something deeply humbling about that realization. Humans often think of oceans, rain, and weather as background conditions surrounding civilization. But prehistoric extinctions suggest the opposite may be true. Climate and water are not scenery. They are the operating system beneath life itself. Forests, animals, and entire evolutionary eras survive only while that system remains within certain boundaries. Once it shifts too far, even dominant species disappear surprisingly quickly. The dinosaurs ruled Earth for over 160 million years, yet they still vanished when planetary conditions changed beyond their ability to recover. Entire marine worlds older than dinosaurs disappeared long before that for similar reasons, tied partly to water and climate instability. And perhaps the most unsettling detail of all is this: many extinction events were not caused by the absence of water, but by too much of it moving differently than before. Oceans warming, rainfall intensifying, floods increasing, atmospheric moisture trapping more heat. The same systems that once allowed life to flourish, becoming powerful enough to erase it. In a world where rain never truly stops, survival may depend less on resisting change than on surviving the moment when the sky itself decides to become something new. If modern humans suddenly appeared inside a world where rain never truly stopped, the most dangerous part would not be the storms themselves. At first, people would probably adapt surprisingly well. Humans are flexible, inventive, cooperative creatures. We survive deserts, frozen tundras, dense jungles, and crowded cities because we constantly reshape environments around us. The first weeks inside a permanently wet world might even feel beautiful in certain places. Endless rivers overflowing through green valleys, mist drifting across forests every morning, waterfalls everywhere, temperatures softened by cloud cover, fresh water seemingly unlimited. But over time, something far more dangerous would begin happening. The rain would stop feeling like weather and start feeling like pressure. A constant force slowly eroding every system human civilization depends on. Because humans do not simply need water to survive, we need balance, and balance disappears quickly when moisture controls everything. Imagine waking up every day beneath a gray sky that never fully clears. Your clothes never completely dry. Wood begins rotting almost immediately unless protected constantly. Metal rusts faster. Food spoils quickly in humid heat. Mold spreads through walls, fabrics, storage containers, even inside homes built specifically to resist moisture. Roads collapse beneath repeated flooding. Rivers shift unpredictably. Soil becomes unstable. Entire hillsides slide apart after weeks of uninterrupted rain. The world slowly softens. Modern civilization is built on the assumption that surfaces remain mostly stable. Permanent rain attacks that assumption constantly. Even now, some of the wettest places on Earth reveal what prolonged moisture does to human environments. Regions with extreme rainfall often battle erosion, flooding, fungal growth, infrastructure damage, crop disease, and transportation failures continuously. Now imagine those problems operating globally and permanently across centuries. Cities would change completely. Many modern urban systems depend on drainage networks designed for periodic storms, not endless rainfall. Underground tunnels flood. Electrical systems fail repeatedly under persistent moisture exposure. Foundations weaken. Sewage systems overflow more often. Coastal regions become especially unstable if sea levels also rise alongside intensified rainfall patterns. Entire neighborhoods might require elevation above wet ground simply to remain habitable long-term. Architecture itself would evolve towards survival against moisture before almost anything else. Human beings would probably build upward, away from the saturated ground. Elevated walkways, raised housing systems, covered transportation corridors, waterproof storage structures becoming more important than decorative buildings. In some regions, daily life might begin resembling combinations of floating settlements, rainforest architecture, and storm shelters merged together permanently. Fire would become psychologically valuable again because dryness itself would become precious. People today rarely think about how much civilization depends on dry storage. Grain, medicine, electronics, books, machinery, fuel, insulation, weapons, paper, clothing, building materials. Almost everything humans create deteriorates faster under constant moisture. Rain changes not only landscapes, but time itself. Objects age differently. Structures decay faster. Maintenance becomes endless, and agriculture may suffer even more severely than cities. Humans became a dominant species partly because agriculture created stable food surpluses. But farming depends on relatively predictable seasonal patterns and controlled moisture levels. Too little rain destroys crops, but too much rain can be equally devastating. Constant saturation suffocates plant roots, spreads fungal diseases rapidly, washes nutrients from soil, and makes harvesting extremely difficult. Some crops would collapse entirely under non-stop humidity. Others might evolve or be selectively bred for wetter conditions. But food systems would still become far more fragile and regionally unstable. Ancient civilizations already reveal how sensitive human societies are to climate shifts involving water. Droughts contributed to societal stress in many historical collapses, but flooding and unstable rainfall patterns have also repeatedly disrupted civilizations throughout history. Rivers that support empires can just as easily destroy them when weather patterns change. A permanently wet earth would force humans into a constant struggle not against thirst, but against oversaturation. And disease would spread differently too. Warm, humid environments favor mosquitoes, parasites, bacteria, fungi, and waterborne illnesses. Stagnant water becomes dangerous. Mold-related respiratory problems increase. Skin infections spread more easily. Food contamination becomes harder to control. Even modern hospitals struggle with fungal outbreaks in certain humid environments because spores travel invisibly through damp air. In a world where moisture dominates every surface, maintaining sanitation becomes a permanent battle. Some scientists already warn that climate change may expand the geographic range of certain diseases, as warmer temperatures and changing rainfall patterns alter ecosystems globally. A permanently wet world could intensify those pressures dramatically. There is also another consequence humans rarely think about. Sunlight itself would change psychologically. Modern humans evolved under cycles of bright skies and darkness that regulate sleep, hormones, mood, and biological rhythms. Extended cloud cover affects mental health, even in present-day climates. Seasonal affective disorder already demonstrates how strongly reduced sunlight exposure can influence emotional well-being. In a world beneath endless gray skies, entire cultures might evolve around preserving artificial light, warmth, and psychological stability against environmental monotony. Imagine generations growing up without truly clear days, children seeing direct sunlight only occasionally through storms, entire mythologies forming around rare bright skies breaking through cloud layers. Human psychology depends more on environmental rhythm than people realize. Endless rain erases rhythm. Days blend together beneath wet skies and filtered light. Time begins feeling softer, slower, heavier. Even sound changes. Rain masks distance. Storms isolate communities. Constant moisture absorbs and distorts environmental cues humans unconsciously rely on. And perhaps most importantly, humans are visually oriented creatures. We like horizons. We like seeing far distances clearly. Endless rain shrinks the visible world. Mountains vanish behind fog. Forests become walls of shadow and dripping vegetation. Rivers expand unpredictably across landscapes. The horizon itself disappears. In some ways, humans might become psychologically more inward in such environments, more local, more community-focused. Travel would feel riskier when weather constantly reshapes terrain and visibility. Maritime cultures might dominate because water routes remain more reliable than unstable roads across flooded landscapes. Floating architecture and amphibious transportation systems could become essential rather than unusual. Entire civilizations might organize themselves around coastlines, river networks, and elevated terrain, while lowlands transform into giant wet ecosystems difficult to control permanently. Yet despite all these difficulties, humans would probably survive. That may be the strangest part of the thought experiment. Civilization would change radically, but extinction would remain unlikely unless rainfall reached truly catastrophic extremes. Humans adapt behavior faster than most large animals because culture evolves far more quickly than biology. We build tools, share knowledge, and redesign environments continuously. In a permanently wet world, human innovation would focus overwhelmingly on moisture control, preservation, waterproofing, fungal resistance, flood management, and environmental prediction. Weather forecasting would become central to survival itself. Entire scientific fields might revolve around understanding cloud systems and hydrological stability with extraordinary precision. Still, adaptation has limits. Some regions could become effectively uninhabitable under endless rainfall combined with warming climates. Landslides, flooding, disease pressure, agricultural collapse, and ecosystem instability might push populations toward narrower, habitable zones over time. Food systems would require enormous energy and technological support. Dry storage would become strategic infrastructure. Energy production itself might shift towards systems resistant to constant storms and moisture exposure. Even warfare would change. Armies struggle in wet conditions. Supply chains weaken. Equipment degrades faster. Visibility shrinks. History already shows how weather alters battles dramatically, even during temporary storms. Permanent rain would reshape conflict completely. There is another, deeper possibility hidden inside all this. Humans evolved during relatively unusual climatic stability compared to much of Earth's past. The Holocene epoch, the period during which agriculture and civilization developed, provided remarkably stable temperatures and rainfall patterns by geological standards. Cities, farming, trade, and modern nations emerged partly because the climate stopped changing too violently for long enough. In other words, civilization may not simply depend on intelligence or technology. It may depend on predictable skies. That realization changes the entire emotional feeling of human history. People often imagine civilization as humanity conquering nature through intelligence. But perhaps civilization is really a temporary agreement with climate, a narrow environmental window where rivers behave predictably enough, seasons remain stable enough, and rainfall stays balanced enough for complex societies to grow. If the rain never stopped, that agreement would weaken constantly. Humans would survive, but the world they built might become almost unrecognizable. And maybe that is the most unsettling possibility hidden inside Earth's ancient rainy eras. The planet itself does not care whether conditions feel comfortable to civilization. Rain falls because physics allows it to fall. Oceans warm because atmospheres change. Storms move where energy drives them. Life adapts if it can. If not, the planet continues anyway. Somewhere beneath endless clouds and permanent storms, humans would eventually understand something ancient creatures already learned long ago. Survival in a wet world is not about controlling the rain. It is about learning how to live inside it without slowly drowning in everything it touches. After looking across billions of years of storms, drowned forests, collapsing oceans, fungal kingdoms, prehistoric swamps, and worlds ruled by endless rain, one unsettling possibility begins to emerge quietly beneath everything else. Maybe Earth was never truly stable to begin with. Maybe stability itself is the illusion. Humans tend to imagine the planet as a fixed stage where life appears, evolves, and builds civilizations against a mostly dependable background. Oceans stay where they belong. Seasons repeat. Forests grow. Rivers follow recognizable paths. Rain comes and goes. But the deeper scientists study Earth's history, the harder it becomes to see permanence anywhere. Continents drift. Oceans open and close. Atmospheres transform. Ice spreads across the planet and then vanishes again. Rainfall patterns move. Forests rise and disappear. Entire ecosystems dominate the Earth for millions of years before collapsing so completely that future species would never guess they existed at all. Even the sky has changed identities repeatedly, and through every transformation, life survives not because the world becomes calm, but because something always manages to adapt before the next change arrives. Imagine watching Earth's entire history compressed into a single night. Oceans forming beneath black clouds. Continents tearing apart and colliding again. Tropical forests growing near the poles during greenhouse eras. Ice eventually covering huge regions of the planet during glacial periods. Seas rising hundreds of feet higher than modern coastlines, then falling again. Entire mountain ranges appearing and eroding away almost like waves. From that perspective, the Earth stops looking solid. It begins looking fluid. The continents drift across the mantle beneath them at rates humans barely notice during one lifetime. Yet over millions of years, they rearrange the entire climate system of the planet. Ocean currents change direction. Winds shift. Rainfall migrates across continents. Deserts appear where forests once stood. Wetlands become mountains. Coral reefs vanish beneath dry land. Stability exists only temporarily between transitions, and perhaps nowhere is that more obvious than in the story of rain itself. Water has moved through Earth's atmosphere continuously for billions of years, but never in exactly the same pattern for very long. During some periods, giant inland seas increased atmospheric moisture across huge regions. During others, colder climates locked enormous quantities of water inside glaciers. Warm greenhouse eras intensified evaporation and storms. Volcanic activity altered cloud formation and atmospheric chemistry. Even the arrangement of continents influences how rain falls, because mountains redirect winds while oceans release heat differently depending on geography. In a sense, every version of Earth creates its own weather personality, and those personalities can change dramatically over geological time. Humans happen to live during a relatively calm interval compared to much of the planet's past. That calmness shapes perception more than people realize. Modern civilization emerged during the Holocene, a period of unusually stable climate following the last ice age. Agriculture spread because seasons became predictable enough for long-term farming. Permanent settlements formed because rivers behaved consistently enough to support cities. Trade expanded because weather patterns remained relatively reliable. The modern human world is built upon assumptions of climatic consistency that may actually be rare in Earth's deeper history. That does not mean prehistoric Earth was constantly apocalyptic. There were long, stable stretches too, but stability on geological timescales still contains enormous environmental shifts compared to human civilization. A climate stable for 1 million years sounds permanent to humans, yet it is only a brief phase in planetary history. And eventually, every phase changes. Some scientists even argue that Earth's long-term climate stability depends on delicate balancing systems operating continuously beneath the surface. Volcanic activity releases carbon dioxide. Weathering processes remove it slowly from the atmosphere through chemical reactions involving rock and rainwater. Oceans absorb heat and carbon. Plants alter atmospheric chemistry. Ice reflects sunlight. Clouds influence temperature differently depending on altitude and composition. The entire planet behaves less like a fixed object and more like a giant, interconnected feedback system constantly adjusting itself. But feedback systems do not guarantee comfort. They only prevent complete collapse most of the time. Sometimes they overshoot. Sometimes they destabilize, and life is forced to adapt afterward. There is something strangely humbling about realizing how little control species truly have over the environments they dominate temporarily. Dinosaurs ruled the Earth for over 160 million years and still vanished. Giant Carboniferous forests covered continents before disappearing almost completely. Marine ecosystems older than dinosaurs collapsed during oceanic crises driven partly by climate and chemistry shifts. Even microorganisms transformed the atmosphere once so dramatically that many existing life forms likely died because oxygen became too abundant. Every dominant form of life eventually discovers that Earth does not remain optimized for anything forever. The planet keeps changing the rules. And rain may symbolize that instability better than almost any other force in nature. Rain connects sky, ocean, atmosphere, rivers, forests, ice, erosion, temperature, and biology into one continuous cycle. It carries minerals across continents. It shapes coastlines. It feeds ecosystems while also destroying them. Too much rain floods civilizations. Too little rain starves them. Storms redistribute heat around the planet constantly. Clouds regulate temperature by reflecting sunlight and trapping warmth. Water vapor amplifies climate changes already underway. The Earth's rain systems are not passive background effects. They are active engines shaping the conditions under which life survives. Which means, if rain changes enough, everything changes eventually. Some researchers studying Earth's future climate suggest warming temperatures could intensify portions of the global water cycle significantly. Warmer air holds more moisture. More moisture can produce heavier rainfall events in certain regions. At the same time, shifting circulation patterns may create stronger droughts elsewhere. The result is not simply more rain or less rain, but instability. Floods where ecosystems evolved for moderation. Dryness where moisture once dominated. Weather patterns becoming harder to predict reliably. Earth has experienced dramatic climate transitions before without human involvement, but modern civilization developed during unusual environmental consistency. That distinction matters. Human systems depend heavily on predictability. Agriculture, infrastructure, trade, transportation, water management, energy systems, all assume certain climate boundaries will remain recognizable. Yet Earth's history suggests boundaries move eventually. They always have. There is another eerie possibility hidden inside the planet's long story of instability. Complex life may survive not because Earth remains stable, but because instability itself drives evolutionary innovation. Mass extinctions destroy ecosystems, but they also create ecological openings for new forms of life afterward. The extinction of non-avian dinosaurs allowed mammals to diversify dramatically. Environmental stress pressures organisms to adapt, migrate, or disappear. In that sense, Earth's constant instability may be partly responsible for the complexity of life humans see today. A perfectly stable world might produce less evolutionary experimentation over deep time. Change creates pressure. Pressure creates adaptation. Adaptation creates new possibilities. That does not make extinction events gentle or desirable. It simply means life evolves inside instability rather than outside it. And perhaps humans struggle emotionally with that idea because civilization teaches the opposite. Humans associate progress with control, permanence, and predictability. Stable governments, stable climates, stable food systems, stable infrastructure. Yet the deeper history of Earth suggests the planet itself never promised permanence to anything. Not forests, not oceans, not dominant species, not even the atmosphere. Somewhere beneath modern cities, ancient rocks still preserve the memory of worlds drowned beneath endless rain long before humans existed. Coal seams remember swamp forests that vanished hundreds of millions of years ago. Fossil shells preserve evidence of vanished oceans. Desert cliffs were once seafloors. Mountain peaks once lay underwater. The earth beneath our feet is filled with evidence that stability eventually breaks. Maybe that is why prehistoric rain feels so haunting emotionally. Rain is temporary to humans. Storms pass, clouds clear. But Earth's deeper history reveals periods when entire worlds lived beneath environmental conditions lasting millions of years. Forests evolved expecting constant moisture. Oceans changed chemistry permanently. Creatures adapted to skies humans would barely recognize. In those moments, rain stopped being weather and became destiny. And perhaps the final unsettling realization is this. Humans often ask whether Earth is becoming unstable, but the planet may answer differently. From Earth's perspective, instability is normal. Continents moving, climates shifting, storms intensifying, ecosystems collapsing and reforming. That is the pattern repeated across billions of years. The truly unusual thing may not be chaos. The truly unusual thing may be the brief calm periods when civilizations have enough stability to imagine the world was permanent all along. Thanks for spending this rainy journey with me tonight. If you enjoyed exploring Earth's ancient storms and forgotten worlds, don't forget to like the video and subscribe to Sleepy Earth channel for more relaxing prehistoric stories and deep time mysteries. Until next time, get comfortable, stay cozy, and let the rain slowly carry you to sleep.